All right, so now we're going to put it all together. So we're going to evaluate the definite integral. Remember, we already evaluated this kind of graphically. We said it was 12. We did this, I think we actually did this one in the last video, but we could do it real quick. This is just going to be 4x from 0 to 3, which means that we would do 4 times 3 minus 4 times 0, and that is in fact 12. And yeah, we got the same area when we looked at it graphically because it's from 0 to 3 and a height of 4. So it'll just be a rectangle that is 3 by 4. All right, well, let's do this one now. What about 0 to 4 of x? So the integral of x would be x squared over 2. And we're going to evaluate that from 0 to 4. So that means we're going to put in a 4. 4 squared divided by 2 minus 0 squared divided by 2. Well, to evaluate this, it's pretty straightforward. 4 squared is 16, and 16 divided by 2 is 8. And then that's just 8 minus 0, so this is just 8. And we can actually, once again, we could also evaluate this graphically. And I'm going to do it because it's really simple. So let's take a look at what this thing would look like from 0 to 4 of just x. Remember, x is just a straight line. It should go right through the origin from 0 to 4. And it also has a height of 4. So this is really just a right triangle with a base of 4 and a height of 4. Well, the area of a triangle is 1/2 the base of 4 times the height of 4. And what is this? This is 1/2 of 16, right? Because 4 times 4 is 16. So half of 16 is 8. And sure enough, we found the same thing, right? That thing has an area of 8, and the integral of that is also 8. So again, not really a proof, but it does kind of show you the reasoning there. So we can apply the same logic to functions like this. This one we wouldn't be able to find the area of just graphically because the graph looks like some type of parabola, right? So we don't have really a way to just quickly identify the area underneath the parabola, but we can now with the antiderivative. So take the antiderivative, we get x cubed over 3 minus simply x squared. And we're going to do this from 2 to 4. So we got 4 cubed over 3 minus 4 squared minus, this is where parentheses come in handy, it would be 2 cubed over 3 minus 2 squared. Okay, let's simplify this in terms of, let's leave the fractions together and let's leave the whole numbers together. So 4 cubed, what is 4 cubed? 4 cubed is 64, so this is 64 thirds, and this is a negative 16. And then if I distribute this negative here, that would be negative 8 thirds, and this negative times this negative would make a positive 4. Okay, so what do we end up with? We end up with 64 minus 8, that's 56. So we got 56 thirds. And negative 16 plus 4 is negative 12. Alright, well, if we wanted to, we can get common denominators here. This will make this whole thing a lot simpler. So, negative 12, well, that's kind of like negative 12 over 1, or multiply top and bottom by 3. We're really looking at 56 minus 12 times 3 is 36 over 3, and 56 minus 26 is 20. So we get 20 thirds. All right, so we've actually now can calculate the area underneath this parabola from 2 to 4, or from any interval, just changing these numbers. It's a pretty powerful tool. Let's go to the next page. Okay, evaluate the definite integral. This again is one that we've already done the antiderivative of. It would simply be 9x squared over 2 minus 2x from 0 to 3. And it would be 9 times 3 squared over 2 minus 2 times 3 minus parentheses. Now if we plug in the 0 here, we could just kind of see what's going to happen, right? This is going to be 0 over 2 minus 2 times 0. This whole thing is just going to be 0. There's no point in giving ourselves unnecessary work here. We're just subtracting a 0. So we really only need to evaluate this. Well, 3 squared is 9, and 9 times 9 is 81. So we're looking at 81 over 2 minus 6. Common denominators, we're going to multiply this by 2 and 2. So this is really like saying 81 minus 12 over 2. Let's see, 81 minus 10 would be 71, minus another 2 would be 69. So this is 69 over 2. And there you go. We've evaluated the definite integral. Let's go to the next one. Okay, this is one that we already did, and we saw that it was going to end up being 0. We could do it one more time here just to see why. Remember we said the graph looks something like that, and so you have some negative and some positive area that cancel each other out perfectly. That would make sense, but let's just do it using the antiderivative. This would be x to the 4th over 4 from negative 1 to 1, and so this is 1 to the 4th over 4 minus negative 1 to the 4th over 4. Well, this ends up being just 1 minus 1 over 4, which is 0. So that worked out exactly like we thought. All right, here's one we already did the antiderivative to. Let's kind of just go through it real quick. In the last video, just to save some time here, we said that this was equal to negative 3 over x minus x from 1 to 2. If you're not sure why, go to the last video and check that out. So when you plug in, you get negative 3 over 2 minus 2 minus, now we plug in the 1, negative 3 over 1 minus 1. Okay, this pretty easy to evaluate here. This is like negative 1.5 and negative 2, so that's really like saying negative 3.5 minus, and inside here we really have a negative 3 minus 1. So lots of negatives here to keep track of, but if you think about this, just do what's inside, you end up with a negative 4, and that really double negative is the same thing as adding. So then you have a 4 and a negative 3.5. Well, that just equals a positive 1/2. And that's it. Let's go to the next page. Okay, this is one that we didn't do in the last video, and that's because this one is a little bit tricky. So to really explain this one, I want us to just think about what the graph of just x squared minus 4 looks like. Not the absolute value of x squared minus 4, just x squared minus 4. So let's think about that over here. X squared minus 4. Well, that should be pretty straightforward. It just looks like x squared, but it's down 4. So it's going to look something like this. Okay. So what would the absolute value of that look like? Well, you could do a t-chart here and just kind of sketch out what it would look like. But basically what's going to happen is any time that this function would kick out a negative, it's actually going to now kick out a positive. So one of the things you want to think about is when does this thing hit 0, because that's when this thing is going to change. So you could see right here in this interval here, even though it's negative normally, now because we're taking the absolute value, it's going to be positive normally. So this little negative interval is actually going to kind of just flip. And so now this is what the absolute value of the same function would look like. And so to determine where that happens, where does this happen? Well, it's just when this thing hits 0, right? Because that's when this thing would stop flipping. Once you start kicking out positive values, it stays the same. It's only when it starts kicking out negative values that it's going to change the sign. Well, when does this thing equal 0? Well, that's pretty easy to determine, because when does x squared minus 4 equal 0? Well, it's when x squared equals 4. And so it's when x equals plus or minus 2. And so this must be negative 2, and this must be positive 2. All right. Well, so the whole point of this is that if we didn't have the absolute value, we'd have this negative area and then some positive area here, because we're going, obviously, till 3. But now we're going to have 2 positive areas. So the easy thing to do here, since we're going from 0 to 3, is to break this into 2 integrals. So we can first start by saying, well, this is the same thing as the integral from 0 to 2 of the absolute value of x squared minus 4 dx plus 2 to 3 of the absolute value of x squared minus 4 dx. Okay. And now we know from looking at the graph, right, if we look at the graph from 2 to 3, it's the exact same thing as x squared minus 4. So we can change this second integral. We can just leave it from 2 to 3 and just drop the absolute values. We don't need them anymore. It's the same thing as x squared minus 4 dx. We already know that, so I'm just going to use parentheses there. This one, however, is not the same, right? Because we're looking at this positive part, not this negative part. So that means that this is very similar to, but the only thing that we'd have to change is the sign. So this is the same thing as negative 0 to 2 of x squared minus 4. Now I'm changing the sign again because we can clearly see that even though we had negative area, we now have positive. Well, and and it's an equal amount of area, right? This would be the same amount of area as this, because it's just this graph flipped over the x-axis. So an easy way to account for that mathematically is just to multiply what you have here by -1, and that will give you this. All right, well, now we can just go ahead and evaluate. We're going to use the same antiderivative here. So we really only need to do that part once. So what's the antiderivative of x squared minus 4? Well, let's leave the negative sign out there. The antiderivative of x squared is x cubed over 3, and the antiderivative of 4 is, or -4, is just -4x. And we're evaluating this from 0 to 2. Plus, let's use the exact same antiderivative, because it really is the exact same function. X cubed over 3 minus 4x, and this is from 2 to 3. All right, now we're ready to just start plugging things in. Hopefully this isn't too complicated what I've done here. It's just about thinking through this reasonably, and you can kind of see how you can manipulate the equations to be exactly what you want and to be able to calculate them. So when you get an absolute value, you need to think about this like this, because you can't really, there's not a quick easy way to take the absolute value of, or the integral of an absolute value. But you could break it up and take the integral of equivalent functions, and that's what we're doing. So let's do this first one. We have a negative. It's going to be 2 cubed over 3 minus 4 times 2 minus, and now I'm going to do the same thing, but I'm plugging in a 0. But look, this would be 0, this would be 0. I don't really need to evaluate that to tell this is all just going to be 0. So this is just minus 0. Plus, when I go over here, I get 3 cubed over 3 minus 4 times 3 minus, let's use parentheses here, 2 cubed over 3 minus 4 times 2. Okay, there's a lot of things going on here, but something interesting is happening. This expression here is the exact same as that expression, but it's important to notice that they're both negative, so they don't cancel each other out because there's 2 of them. But we are going to be able to combine some, some like terms, or just kind of think of this as being doubled. Maybe that's a little bit too advanced. It's something you'll see later on. It's just kind of an algebra technique that you see that you really have 2 of these, so you can just kind of double it. But let's just go ahead and evaluate everything that we have, just kind of straightforward here. What do we really have? We have a negative. 2 cubed is 8. Thirds minus 8. The minus 0 obviously doesn't matter. Plus 3 cubed is 27, but divided by, you could kind of think of that as 3 to the 1. So that's really like 3 squared, or 9, minus 12, minus another 8 cubes minus 8. All right, so let's go ahead and distribute these negatives. This is really like saying negative 8 thirds plus 8 plus 9, negative 12, plus 8 thirds plus 8. I'm sorry, that's a negative 8 thirds still here. Okay. I'm going to do the parts that are easy for me. These 2 things together just make a negative 16 thirds. And then we kind of just work through all of this. You got an 8 plus 9, that's 17, minus 12 is 5, plus 8 is 13. And if we want to common denominators, we could do that real quick. And so what we really have here is like saying 39 minus 16 over 3, which is 23 thirds. Okay, I get it. A lot of work. But there's no single step here that is actually too difficult for you. The only thing that is a little challenging is maybe how to start. And so I'm going to remind you, you have to think about what this thing looks like as a graph. If you were to plug this thing into a t-chart, you'd get this same thing that I have here in blue. So the point is to recognize what the absolute value does to a function. And all it does is it changes negatives to positives. Because it doesn't change positives at all. They stay positive. So that's why the part that's positive of this graph is still positive. It's the only thing that changes is the part of the graph that's negative. So think about it graphically If you need to, sketch it out graphically and then reason through how you could calculate those two areas. So I calculated this area and then just took the opposite of it. And this area I just calculated the exact same way that you would whether it was an absolute value or not, right? Because it's the same. So if you reason through that, it should be pretty simple to set up these different problems. Definitely going to want to kind of practice that kind of idea a few times, maybe make up a few problems like this, or you can find some in the book or on Khan. But this is something you got to be familiar with doing. All right, I'll see you guys on the next video.